expertise of those who craft these indispensable tools. As we appreciate the elegance of a well-designed knife handle, we also recognize the profound impact that engineering and physics have on elevating the functionality and efficiency of this age-old instrument. Furthermore, the physics of friction plays a pivotal role in the performance of a knife. The interaction between the blade and the material being cut involves complex frictional forces. Engineers take into account the coefficient of friction, material properties, and the cutting motion to optimize the blade's performance. Reduced friction ensures smoother cutting and prolonged edge retention. Moving beyond the broad strokes of friction, let us delve deeper into the intricate physics that govern this essential aspect of knife performance. Engineers pay meticulous attention to the coefficient of friction, a dimensionless quantity that characterizes the interaction between two materials in contact. By selecting materials with specific coefficients, they can fine-tune the frictional forces at play during cutting. Material properties, such as hardness and surface finish, are also critical considerations. The interaction between the blade and the material being cut is akin to a microscopic battle, where the surface roughness and hardness of both materials determine the effectiveness of the cut. Engineers analyze these properties to optimize the blade's design, ensuring it is tailored to excel in specific cutting applications. The cutting motion itself is a ballet of physics in action. Different cutting techniques, whether it be slicing, chopping, or dicing, generate distinct forces and stresses on the blade. Engineers employ principles of mechanics to study these dynamic forces and design blades that can withstand the rigors of various cutting styles. The goal is not only to create a sharp and durable edge but also to enhance the knife's versatility across different culinary or practical applications. Reducing friction is not solely about creating a smoother cutting experience, it also plays a crucial role in edge retention. Friction generates heat, and excessive heat can compromise the hardness of the blade. Engineers must strike a delicate balance to minimize friction-induced heat during cutting. This delicate equilibrium involves the selection of appropriate materials, optimal edge geometries, and, in some cases, incorporating features like non-stick coatings to mitigate friction and heat buildup. Consider also the microscopic landscape of the blade's edge. Engineers leverage principles of tribology, the science of interacting surfaces and relative motion, to understand the wear and tear on the blade during use. This understanding informs the design of blade profiles, bevel angles, and edge geometries to maximize the knife's lifespan. In the quest for prolonged edge retention, engineers explore advanced surface treatments and coatings. Techniques like cryogenic tempering and nitriding alter the surface properties of the blade on a molecular level, enhancing its resistance to wear and corrosion. These processes are rooted in the principles of materials science, where engineers manipulate the microstructure of the steel to achieve desired mechanical properties. In essence, the optimization of a knife's performance involves a symphony of physics and engineering, from the macroscopic considerations of material selection and handle design to the microscopic realm of frictional forces and edge geometry. Every aspect is a testament to the marriage of science and craftsmanship. As we appreciate the elegance of a well-designed knife, let us marvel at the invisible forces and scientific ingenuity that make it a true work of art. Let's not forget about the physics behind the heat treatment process. Achieving the right balance of hardness and toughness involves precise control over the heating and cooling cycles. Engineers employ principles of thermodynamics to transform the molecular structure of the steel, ensuring the blade's ability to withstand stress and deformation. Delving deeper into the realm of heat treatment, the process is a sophisticated dance with temperature and time. Engineers meticulously orchestrate the heating phase, often subjecting the blade to extreme temperatures, sometimes exceeding 1,800 degrees Fahrenheit. This elevated temperature allows for the steel's molecular structure to transition into a more malleable state, making it receptive to subsequent manipulation. The critical